All right, well, good afternoon, everybody. It looks like it's 1 o'clock and time for us to begin. So I have 4 problems from the extra practice problem set that I want to go over. And then one of you have already submitted a homework question that you want me to look at. And so I'm happy to do that. And we'll begin with number 28 in the extra practice problem set. So let me click that. All right, so with this question, this is all about navigating between the grams and the number of moles and the number of particles. If I could spell particles, okay, that's a T. All right, so remember that in order for us to go from grams to moles, what we need is the molar mass. That's how we convert. That's what we use as a conversion factor when you're going in between the number of grams and the number of moles. And a different conversion factor when you're translating or going between the number of moles and the number of particles, and that's Avogadro's number, okay? So to answer this question, we're gonna use both of these conversion factors because we start here. We know the mass of CO2 in grams, and we wanna end up here at the number of particles, says how many molecules of CO2 will be produced, okay? So what we need to do is we need to convert grams into moles, and we'll do that by dividing by the molar mass. And then once we get the number of moles, then we convert that into the number of particles, right, by just multiplying by Avogadro's number, because by definition, 1 mole of something is an Avogadro's number of that thing. There's one additional step that we need to make, though, in this case, because we have kilograms as a mass instead of grams. And the other thing that we're going to need to know is we're going to need to know the molar mass of carbon dioxide. So remember how to come up with that. I'm going to simplify it a little bit. The average atomic mass of carbon is basically 12. And then the average atomic mass of oxygen is 16, basically. And there's 2 of them. Okay, so 12 plus 2 times 16, which is 32. So 12 plus 32 equals 44. So we're going to say that the molar mass of CO2 is 44 grams per mole. Now, of course, you could look up the exact numbers in the periodic table, but you start to memorize the approximate atomic masses of several of the elements, and I, 9 times out of 10, if you round to the nearest whole number, it's not going to affect the calculation to some point that won't be within the acceptable range. So feel free to do that. If you get the wrong answer, you might go back and do it the more detailed way. But I doubt that was the issue. Okay, so getting back to the solution here. So I start with the fact that I have 4.9 kilograms of CO2. All right. Well, I know that by definition, 1 kilogram is 1,000 grams. So now kilo of CO2. So kilograms of CO2 cancel. So now I have grams of CO2 as my units. And I need to convert that into moles. So I know that by definition, 1 mole of CO2 is 44 grams. So 44.0 grams of CO2. So now units of grams of CO2 cancel. So now I have units of moles of CO2. All right. And we need to go all the way to particles. So that's where Avogadro's number comes into play. So again, I know that there are 6.022 times 10 to the 23rd CO2 molecules in every 1 mole of CO2. That's the definition of a mole. And Avogadro's number of something is a mole of that thing. So moles of CO2 cancel. And so when I punch all that into my calculator, you will get units of CO2 molecules, which is what we are asked to find. So punching that into your calculator, we got 4.9 times 1,000 times 6.022 times 10 to the 23rd. I hit enter, and then I divide by 44. I hit enter, and I get 6.71 times 10 to the 25th. So 6.71 times 10 to the 25th CO2 molecules. All right, so let's just punch that in here. So 6.71 times 10 to the 25th molecules. And I'll clear away all the drawings here. We'll submit the work. And that is correct. Okay. All right, so that's number 28. Okay, so the next one that I want to look at, I'm going to move down to number 46. All right, this is a stoichiometry problem, number 46. All right, what I'll do is I'll handwrite it out first, and then we'll put it in using the scaffolding. Okay, so we want to find the mass of nitric acid, which is HNO3, and that is required to neutralize, which means to completely react with 4.3 grams of calcium hydroxide. So if I have 4.3 grams of this substance, what mass of this substance do I need to completely react? Okay, well, one of the things that we're going to need is we're going to need to know the molar mass of calcium hydroxide. So there's the calcium in there. So let me bring up the periodic table just a second. Okay, so calcium is, I'll start drawing here again. So calcium is right there. So that's, again, I'm just going to estimate. We're going to say it's 40. Okay, and then the formula is CaOH2. So I've got 2 oxygens, so 2 times 16 plus 2 times 1 for the hydrogens, right? That's calcium hydroxide. So 40 plus 32 is, let's see, 72. And then plus 2 more is 74, okay? So that'd be 74 grams per mole is the molar mass of calcium hydroxide. Okay, so just to make sure, we can kind of look down here, and we're going to use in the actual scaffolding 74.1, so I might as well just use that whenever I do the calculation. Okay, but that 74.1 is the molar mass for calcium hydroxide. All right, so remember, with these type of questions, you begin with a number that you're going to use, or that you're given that's not a conversion factor. Well, that would be the mass of calcium hydroxide. So that's where I'm going to start. So I've got 4.30 grams of calcium hydroxide. Okay, and the first thing I need to do is convert that into moles. Remember the stoichiometry roadmap. You can't go directly from grams of one thing to grams of another. You have to go through moles. So that's the first thing we're going to do. We're going to say, well, 1 mole of calcium hydroxide is 74.01 grams of calcium hydroxide. Okay, so units of grams of calcium hydroxide cancel. So now I have units of moles of calcium hydroxide. And so now remember, what you need to do is I need to stop talking about this substance and start talking about this substance, because that's what I'm being asked about. I'm asked the grams of nitric acid. That's my target, right? So I look at the mole ratio. So I've got a 2 for the nitric acid, and there's a 1 implied there out front of the calcium hydroxide. So 1 mole of calcium hydroxide on the bottom, so it will cancel, is or reacts with 2 moles of nitric acid, HNO3. So my units of moles of calcium hydroxide cancel. So now I have units of moles of HNO3. Okay, so I'm not quite there yet. I have moles of nitric acid, but I am asked to determine the grams of nitric acid. So I also need the molar mass of nitric acid. So for nitric acid, the hydrogen has basically a 1 gram per mole. The nitrogen is basically 14 grams per mole. And then there's 3 oxygens, so 3 times 16. Okay, so let me punch that into my calculator. So 1 plus 14 plus 3 times 16, 1 plus 14 plus 3 times 16 equals 63, okay? And I'll just check down here to see if there's a 63 anywhere. There it is, 63.02, so that's the one that I'll use in the scaffolding, okay? But nitric acid has a molar mass of 63 grams per mole. So again, using that as a conversion factor here, 1 mole of HNO3 has a mass of 63, and I'll go ahead and use this number, 63.02 grams of HNO3. So now my units of moles of HNO3 cancel, and I have the desired units. I have something in grams of HNO3. Okay. So let me just punch all that into my calculator. So 4.3 times 2 times 63.02, hit enter, and I divide that by 74.01, hit enter. There's nothing else in the denominator. So I get 7.32 if you round to 3 sig figs, so 7.32. And with these, you can always kind of look. And so here's a 7.31, Okay, so that's a reasonable answer. At least it's down here. Okay, so that's the one I'm going to choose whenever I punch in the answer. All right, so just putting all this in the scaffolding then. So let me change my. So the starting amount is 4.3 grams of calcium hydroxide. And by definition, 1 mole of calcium hydroxide is the 74 point. Oh, you know what? I did the math wrong. I noticed that I substituted in the wrong number. I just didn't read it correctly. 74.1 instead of 74.01. But the method is the same, and it's a trivial difference. But 74 grams of calcium hydroxide. So that will make those units cancel. Okay. And so, as I said, now the next step is to convert between talking about the calcium hydroxide into talking about the nitric acid. So 2 is the right ratio. 2 moles of HNO3 react with 1 mole of calcium hydroxide. Where'd it go? There it is. Okay, so now units of calcium, moles of calcium hydroxide cancel. All right, so one more thing we need to do is convert from moles of nitric acid into grams of nitric acid. So 1 mole of nitric acid, we said was 63, so 63.02 grams of nitric acid. Okay, so now I have the units that I'm looking for. So I can do my answer bar here, or answer box. And as we figured out, 7.31 is the amount. Okay, so clear all this away. We'll submit the work. And we're correct on that one too, okay? All right, so that one was number 46. So the next one that I want to do is 55. Okay, so how many moles of nitric acid will be produced from the reaction of 45 grams of NO2 with excess water in the following chemical reaction? So again, this one is just a fairly garden variety stoichiometry problem. We know the mass of one reactant, and I'm told I have an excess of the other reactant, and we want to figure out how much of this product will be made, okay? So we may need a couple molar masses, and that's about it. So let's think about that. Well, I tell you what, we'll plug in the molar masses as we plug along. So we're going to start with this 45 grams of NO2. Okay, so that's going to be our starting point, 45.0 grams of NO2. All right, and so I can't go from grams to grams, or even from grams of this reactant to moles of this product. I got to first of all convert this mass of the reactant into a number of moles of that reactant. Okay, so 1 mole of NO2 is 14 plus 32. Remember, 16 times 2, so 14. I guess I'll write that out. 14 plus 2 times 16. Okay, so that's 32. So 46. Let's see, 14, 32. Don't want to make a stupid mistake. Yeah, so 46 grams per mole. So 46, and we'll say 0.0 grams of NO2. So that means my units of grams of NO2 will cancel. All right. So now I want to stop talking about NO2 and I want to start talking about HNO3. It says how many moles of HNO3. So I'll use these mole ratios from the coefficients in the balanced reaction equation to do that. So this reaction tells me that I consume 3 moles of NO2 for every 2 moles of HNO3 that are produced. So the units of moles of NO2 cancel, and my units right now are in moles of HNO3, which is what I want to find. Okay, so now I'm ready to plug in the numbers into my calculator, right? So I can do that. We got 45 times 2, enter, and I divide that by 46, enter, and divide again by 3, enter, and I get 0.652 if I round to 3 sig figs. So 0.652 moles of HNO3, okay, is what I think the answer is. So let's just punch that in to our answer box over here. So 0.652, clear all that away, submit our work. And once again, we're good to go there. Okay. All right, so that was number 55. Okay, so the last one that I want to do in this problem set today is number 67. This is a limiting reactant problem. Okay, so in this one, it's not as lengthy as some of the limiting reactant problems that we go over, because we start with the number of moles, but the technique of determining the theoretical yield is the same, except for we're missing one step. We don't have to convert grams into moles in order to answer this question. Okay, so what we're told is that we have 7.5 moles of ammonia and we have 8.2 moles of oxygen. So one of these is going to run out first. And we just need to figure out which one is going to run out first. And the recommended way of doing that is just go ahead and figure out how much product. And there's two products, and this one it designates, which one we care about. But if it hadn't, you just pick one. But in our case, we're told that we want to figure out how many moles of water will be formed, right? So we're going to do that with each one of these starting numbers, two different calculations. And at the end, we'll see that one of them results in a smaller amount of water being produced. So that identified the limiting reactant, and it also identifies the theoretical yield, which is the actual answer to this question. When you get the theoretical yield, you've also got the answer to the question in units of moles. So here we go. So 7.50 moles of ammonia. All right. And so from the balanced reaction, I see that there are 4 moles of ammonia used up to produce 6 moles of water. So 6 mole of H2O from 4 mole of NH3 in this reaction. So units of moles of NH3 cancel. And my answer will be with units of moles of H2O. Okay. So punch that in. So 7.5 times 6, enter, divided by 4, enter, and you get 11.25 moles of water. All right, so that's one possibility. I could get 11.25 moles of water, but that is if the ammonia runs out first. I need to do the same kind of calculation with this 8.2 moles of oxygen, and then I'll compare the results. So 8.20 moles of O2, okay, and the mole ratio there is a little different. I use 5 moles of oxygen for every 6 moles of water that are produced. So 6 mole of H2O use up 5 mole of O2. So units of moles of O2 cancel. So I will get units of moles of water. And again, what I'm going to end up doing is comparing these two numbers of moles. So 8.2 times 6, enter, divided by 5, enter, and I get 9.84. 9.84. Okay. Well, you can see here that this is the smaller number. And so that means that this is my limiting reactant, and this is the theoretical yield. So theoretically, this is the most water I'll get based on the amounts of starting materials that I have. Okay, so I'm going to punch in the 9.84 right there. And I'm going to clear away all my work and submit the answer. And once again, we got that one right too. Okay. All right, so that was number 67. Okay, so now if you'll bear with me for a second, I'm going to go to the homework assignment. Just one of you asked about number 5, some issues with number 5. So we'll go to the homework assignment, unit 2 homework. We'll look at number 5. Okay. Oh yeah. So somebody else came to me earlier in the week with a question about this one. So let me just kind of demonstrate how to set this one up. So we are asked to determine the number of moles of silver that are in a certain mass of a compound that contains silver. Okay. So specifically, we're asked about the moles of silver in a compound that contains silver. All right. So one thing we're going to need is we're going to need the molar mass of that compound. Okay. So let me flip over to the periodic table. So silver, the formula is, if you don't remember, the formula is Ag2O. So silver is 107.9. So 107.9, and that's all times 2. And then I'm going to add in the 16, just I'll estimate there. So 107.9 times 2 plus 16 equals 231.8. Units are grams per mole. Okay. So I'll use that in my calculation here, the 231.8. All right, so we have a mass of that compound, and what I need to do is convert that into moles of the compound, and then I need to do a mole ratio between the moles of silver per mole of compound. All right, spoiler alert, it's 2 to 1. So we've got the 88.2 grams of the compound, Ag2O. All right, and I just said that in 1 mole of Ag2O, there are 231.8 grams of Ag2O. So units of grams of Ag2O cancel, and right now I have moles of Ag2O. All right, so here's where I get at the actual answer, because notice that from the formula, you got 2 silvers for every 1 compound unit as a whole, right? So that's the key. So there are 2 moles of Ag in every 1 mole of Ag2O. So units of moles of Ag2O cancel. And so whatever your answer is, it will have units of moles of silver, which is what you're asked to find, okay? So keeping in mind, the question that you have in your assignment may not start with 88.2 grams. So I'm not even gonna finish this one because I think that this number changes from student to student, but this is the method that you would use to set it up. You just start with that mass, convert it into moles of the compound, and then go into the formula to get the mole ratio of, in this case, silver to the 1 mole of the formula unit as a whole, right? And that's how you solve for it. Once you get that number, that's what you punch in. Okay, so let me take a drink of coffee here for a second. All right, so that's pretty much everything that I wanted to cover. And if anybody else has questions, I'll let you you can take yourself off mute and just ask, or you can punch it into the chat box, but we'll just pause for a second. Okay, having heard no questions, I'll go ahead and we'll stop there. Oh, wait, here we go. Could you run through number 44 on PP? And I think what you mean by PP is the extra practice problems. Practice problems, yeah. Okay, so we'll go back to the practice problem set, and we'll go back to practice. We'll go to extra practice. We'll go down to number 44. Okay, determine. So can you put a yes or no answer? Is this the right one? Is this the one you want me to do? Yes, okay. All right, so determine the mass in grams of butane C4H10 that are required to completely react to produce 8.7 moles of CO2 according to the following combustion reaction. All right, and it is balanced, okay? So I'm gonna just write it out and then we'll put it in the scaffolding, perhaps. We'll see. Okay, so basically we want to go from the moles of the product, right? So we start here. We know this is like our A, and we want to know, and B would be the grams of this reactant, this butane. Okay, what we know in this case is the amount of the product. Okay, so we're going to kind of work backwards, right? So what we know is that we have 8.7 moles of CO2. Okay, and then I use the mole ratio. So there's 8 moles of CO2 produced for every 2 moles of butane used. So I put the 8 moles of CO2 on the bottom because that's what I want to cancel. So 8 moles of CO2 for every 2 moles of C4H10. So moles of CO2 cancel. All right, so now I have moles of this reactant, but what I want are grams of that reactant. So I need the molar mass of that. right? Well, that's going to be 4 times 12 because there's 4 carbons, and 10 times 1 because there's 10 hydrogens. Okay, so that is 4 times 12 plus 10, 58. Is that down here somewhere? 58.14. Yeah, we'll use that. 58.14 grams per mole. Okay, so that's what we're going to use here, because by definition, 1 mole of C4H10 is 58.14 grams of C4H10. Okay, so units of moles of butane cancel, and right now I have units of grams of butane, C4H10, which is what I want. Okay, so we'll just plug all that into our scaffolding here. So we start with 8.7 moles of CO2. Where'd it go? Moles of CO2. And then I just do a mole ratio. So I want moles of CO2 to cancel. So according to this reaction, 8 moles of CO2 require 2 moles of butane. All right, so now I just need to convert from moles of butane into grams of butane. So but the definition of 1 mole of butane is it has a mass of 58.14 grams of butane. So now I have the units that I need, grams of butane. So I'm ready for my answer. So the answer will be in units of grams of butane. Okay, so I can punch all this into my calculator. So 8.7 times 2 times 58.14, and I hit enter, and then I divide by 8, and I get 126.5. So is that up here? 126.5. Well, with rounding to 3 sig figs, it's just going to be 126. Okay, so I think that's right. So let's clear it away and we'll submit our work. Let's see. Okay, so there you go. So again, you may have started with a different number than 8.7 in your problem set, so just be aware of that, but the method is the same. Okay, so hopefully that was helpful. Anybody else have a question you want me to go over? Going once, going twice. All righty. Well, thanks everybody. I hope you'll have a good weekend, and we'll look forward to seeing you on Monday.